G'day everybody, in this video we're going to be looking at a new concept called magnetic flux. It's the first concept which really underpins inquiry question 3, which asks what happens to stationary and moving charged particles when they interact with an electric or magnetic field. And our focus here is going to be on describing how magnetic flux can change with reference to this relationship here. So the key point of today is to really look at what is magnetic flux, and then also look at how we can change magnetic flux. That will allow us to unpack the syllabus dot point in a little bit more detail in class. So first off, magnetic flux, you'll see it written as a capital Phi. That is magnetic flux. And essentially what it is how much magnetic field is passing through a set area. So we've shown the density of magnetic field before by drawing lots of field lines all bunched up together if there's lots of magnetic field inside a small area. In other words, high density of magnetic field. Or if there was some low density of magnetic field, we would draw less field lines in that same set space. And so magnetic flux can be calculated as B parallel A, where B is the magnetic field, and A is the area through which we're looking at that magnetic field passing through. You'll notice here that we have B parallel though. So when we're saying B parallel, we're referring to the magnetic field when it is parallel to vector A. It's shown in each of these diagrams in the center. Essentially, vector A is the normal to the plane of the area. So if we have our area space here, A is perpendicular to that. In this scenario, in B, we can see all of these magnetic field lines following the same direction as the normal to that area, which means that these are all passing directly through the area that we're focused on. And by multiplying the magnetic field strength by the area that we're looking at, this would allow us to calculate for magnetic flux. However, in scenarios that we are going to encounter, you won't always have the magnetic field moving perpendicularly to the plane of the area that we're focused on. Therefore, we get cos theta starting to get involved. And cos theta will account for the angle between the magnetic field and the normal to the plane area. In other words, cos theta will calculate the component of the magnetic field, which is parallel to vector A. Let's have a look at scenario B first. We should be able to appreciate that this diagram shows a scenario where you would have maximum magnetic flux, and that is because cos 0 is equal to 1, which if we were to substitute into this equation, would lead to the maximum value magnetic flux. Down the bottom in scenario C, we can see that the magnetic field is parallel to the plane and perpendicular to the normal. In this scenario, we would have the minimum amount of magnetic flux, and this is because cos 90 is equal to 0. Technically speaking, minimum flux is 0 flux. And in scenario A, we get a little bit of a mixed bag and a range of fluxes that could occur, not the maximum, not the minimum, but rather everything in between. And this is because you're going to end up with an angle in scenario A that is greater than 0 but less than 90. And as a result, when you substitute that into cos theta, you're going to get a value which again is greater than 0 but less than 1. And so that acts as a multiplier when you multiply that with the magnetic field strength as well as the area, which will yield you a result above the minimum because you're not multiplying by 0, but it will give you a result below the maximum because you're going to be multiplying by a value which is less than 1. So how can we change magnetic flux? Because this is going to be quite an important concept moving into the rest of Module 3. Essentially, there are 3 ways because there are 3 variables in the magnetic flux formula. We could change the shape of the area that you're looking at. If you change the shape, you change the amount of area, and therefore you would change the amount of flux. You could also change the magnetic field that's passing through that area. That's quite closely related to concepts that we'll look at around transformers. But to change magnetic field, you would just be either increasing or decreasing B. You can also change the angle of the area to the field. So that would be changing theta. And this change is quite closely connected to concepts around motors and generators. Thank you very much, everyone. We're going to build on some of those flux concepts in class. But when we move on to the next video, we're going to be looking at 2 fundamental physics laws Lenz's law and Faraday's law, both of which help us to understand a new concept which we'll start to look at, which is all about electromagnetic induction. But until then, have a good one.